Next, we're going to talk about that problem of if we don't have an exact equation, what do we do about it? Unfortunately, there actually is an equation or a way that we can make equations exact when they aren't. So I'm going to write those rules here real quick, and then I'm also going to write the same thing in our steps. I'm just going to write like longer form here so you actually know how to put all the pieces together, and a quick reminder of the things to calculate on our steps. So if m dx plus n dy is not exact, we're going to go ahead and compute m sub y, which is that partial derivative dm dy, and n sub x equal to the partial derivative dn dx. And you have to do this anyhow to make sure they're exact. I'm just giving them names right here so that we can write them in like a formula. And then we're going to check two different quantities that might help us out. So we're going to check m sub y minus n sub x over n. Or we're going to check n sub x minus m sub y over m. I can't ever remember these. I don't expect you to memorize these. You will have this quantity written for you on an exam if you need to use it. But the first one, m sub y minus n sub x over n, we want to check if it depends only on x. And if that's true, then the thing that's going to help us out is going to be mu equal to e, the integral of m sub y minus n sub x over n. Alternatively, we can check if that n sub x minus m sub y over m depends only on y. In that case, mu equal to e, the integral of n sub x minus m sub y over m, with respect to y, the other one being an integral with respect to x. That's going to be the thing that helps us out. And then regardless of which mu you choose, if you multiply it through your differential equation, it will now be exact. So mu m dx plus mu n dy equal to 0 is going to be exact. And so I just want to roll back to the steps we wrote out, and so I'd like you to go back in your notes as well to that empty space 2b we came up with, and we're just going to add the rule that we need to make it exact. Which is multiplying by either e to the integral m sub y minus n sub x over n dx, or e to integral n sub x minus m sub y over m dy. Sorry, I should stay there for a second so that you can actually put it in your notes. So it can be a little bit difficult to keep track of all the m's and n's. Don't need to memorize it. Just know how to use it. So that's going to be our approach to make something exact. And I'm going to show you an example where we need to do that. So xv dv dx plus v squared equal to 32x is going to be an equation that describes a chain falling at speed v at its current length y. So a picture of that is that we've got like this cable, and for whatever reason it's got a big hole in it and some kind of anchor and a chain attached to that anchor. Chain goes through the hole, and the chain can fall through the hole. I'm a mathematician, so I don't know why you would care about that, but I trust that you all can come up with a good physical reason that we would care about this chain in a hole. The way it's described to us, x is going to be this position of where the length of the chain has gone, and then v is the speed it's going. And I'm so sorry, I wrote current length y. That's definitely x. That's the length of the chain. I don't know why I did that. But that's the differential equation we're going to be trying to solve. And I'm going to set it up in exact form, show you that it's not exact, and then we'll probably take a break and then start the next video actually going through the steps of solving it. But rearranging everything the way we need it to be, we're going to take this xv dv dx plus v squared equal 32x and rearrange it. So we've got xv dv equal to 32x minus v squared dx. So similar to separable equations, we do kind of break that derivative apart. Difference being that we don't really care which variables end up with dv or dx. And then we just put it all on one side. So we've got v squared minus 32x dx. I'm moving everything on the right over to the left, plus xv dv. And here, this is kind of like my dy that I used to have. It's just called dv now. And I'm sorry, that's equal to 0 once I move everything over to the left. And so now that it's in this form, it does look like an exact equation. I've got something times dx plus something times dy or dv. And in this case, my m, the thing multiplying dx, is going to be v squared minus 32x. And my n, the thing multiplying dv, is going to be xv. And we're going to have to go ahead and check if it's exact. It's not going to be exact, but you wouldn't know that if it was a random problem assigned to you. So first we take the derivative of the thing that was attached to x with respect to the other variable. So dm dv, or the derivative with respect to v of that v squared minus 32x. And when we take that partial, we treat x like a constant, so this derivative is just going to be 2v. And just so you know, the other notation for this dm dv is going to be that this is m sub v. And then we compute dn dx, the thing that multiplied the other variable, we take the derivative with respect to x. That's going to be d dx of that vx. And we just treat v like a constant, take derivative with respect to x as 1, so we just get v. These two things are not the same, so it's not exact. And that second quantity I calculated is that n sub x. That's just the different notation for taking a derivative. So the problem we have is that our equation is not exact. And so we're going to have to try and make it exact, which I'm going to go ahead and hit pause here. And then in the next video, we'll actually go through the steps of when you have a not exact equation, how are we going to fix it and then solve it.